Hi there. Today we'll be learning about the VSEPR theory, or the valence shell electron repulsion theory. So by the name itself, we understand that it talks about the valence shell, so the outermost shell of the atom, and the electron pair repulsion. So whenever we have an electron pair, it is going to repel other electron pairs. Why? Because both of them have a negative charge. So the theory basically says that electron pairs in any way, whether it be bonded pairs or lone pairs, repel each other, and that a molecule adopts the shape that minimizes the repulsion and maximizes the stability, or in other words, minimizes the repulsion and maximizes the distance between the electron pairs. So now let's take a look at a little calculation. So the repulsion between lone pair and lone pair electrons is going to be much greater than repulsion between a lone pair and bond pair, which will be greater than a bond pair and a bond pair. So let's take the example of H2O. So first of all, let's draw the Lewis diagram for H2O. So we have oxygen in the middle, and then we've got hydrogen over here, and then two. So as you can see, there are two electrons that are in each pair. So these electrons, what they're going to do is that they're going to repel the other atoms, whether it be bonded electrons or it be other lone pair electrons. So if we put this in a 3D manner, we'll see that the water molecule arranges itself with oxygen in the middle, hydrogen over here, another hydrogen coming out of the plane over here like this, one bond pair that goes in the plane, so we'll draw the bond pair like that, and one bond pair like that. So the reason for the increase in bond pair, lone pair repulsion is because these lone pairs, they occupy a lot of space, right? They're not bound, they're not restricted to any area. One could even say they are delocalized. However, the electrons that are in the bond pair, they cannot move around that much, right? They're bonded. So that's literally why they form that bond, because they've connected to each other. So bond pairs do not repel each other that much. However, when it's a lone pair and a bond pair, there you would have a lot of repulsion, because again, the lone pair would occupy a lot of space, and when it's lone pair, that would be the most amount of repulsion, since both of the pairs now occupy a lot of space. Let's take another example. Let's take CH4. So a quick diagram of CH4. Now if we arrange this, we get a very similar looking geometry. So a hydrogen like that, one hydrogen coming out of the plane, and one hydrogen going inside the plane. Now you might say that the geometry, since the geometry for carbon, for methane and water is same, one could argue that the angles must also be same. However, like we've already said, lone pair repulsion is much greater. So what's going to happen is that these two hydrogens, they're going to be pushed together inside, while the other hydrogens in methane, they're just freely floating, right? Because these are bond pairs, they won't have as much repulsion. So what happens is that we see that in the tetrahedron formed by the methane, there is an angle of 109 degrees, 109.5 degrees between each pair, while here we only see 104.5 degrees between the hydrogens. Again, why? Because the lone pairs take up a lot of space. Now let's take a look at something called the steric number. So the steric number is a little tool that we have to define the shape, well, not the shape, the geometry of any given molecule. So first of all, it takes the number of sigma bonds. So we'll learn what a sigma bond is, plus the number of lone pairs on the atom, on the central atom. So a sigma bond is nothing but a single bond. So just a single bond is equal to a sigma bond. It's just another way of saying a single bond. Now let's take a look at what this could mean. Let's take another example. Let's take NH3. So this is ammonia. Now we have ammonia, we have nitrogen as the central atom, and then one hydrogen like that, another hydrogen coming out of the plane, another hydrogen going in the plane, and then a lone pair in the middle. So here we clearly see that there is a single bond between the first hydrogen, a single bond between the second hydrogen, and a single bond between the third hydrogen. So how many sigma bonds do we have? Well, we clearly have 3 sigma bonds plus 1 lone pair on the central atom. That gives a steric number. So the steric number for ammonia would be 4. Now let's take a look at how we can apply the steric number. So a steric number of 2 is going to give you the geometry. Remember, there's just a reminder that geometry does not equal to the shape of the molecule. The geometry is just how the electron bonds or the electron pairs are arranged. So whether it be a lone pair or it be a bond pair. However, the shape is how the atoms are arranged. So let's take back to the example of water. We see that the bond pairs are arranged in a tetrahedral shape, while the atoms are only bent. So there's hydrogen, oxygen, and then hydrogen. However, if you take a look at methane, we see that the shape is also tetrahedral because the hydrogens are placed in 4 corners. If you take a look at ammonia, then we see how the geometry is again tetrahedral, but the shape of the molecule is T-shaped because the way the hydrogens and nitrogen is arranged looks like a T. So back to our topic. So when the steric number is 2, the geometry is going to be linear. So let's take a quick example. If we have carbon dioxide, it gives us a steric number of 2. So that's why we have this. Now remember, the second bond that is formed here is the pi bond between carbon and oxygen. And whenever we count sigma bonds or single bonds, we do not take in account the pi bonds. So here, the number of sigma bonds is just 2, and then we have no lone pairs on the central atom. So that is 2 plus 0, that gives us 2. And that is why this is 180 degrees. Now, a steric number of 3 would give you trigonal planar. So this is just a central atom with 3. So let's say if you have BF3, so this is boron in the center and then fluorine on the outer edges, and then the angle between them is 120 degrees. Now, of course, if you had another, let's just take A and B. If you had something like this, then of course the electron in the lone pair would push the B atoms together and reduce it to somewhere less than 120 degrees. Now, a steric number of 4 would give us tetrahedral, like we've already seen in our example, tetrahedral. Steric number of 5 would give us trigonal, pyramidal, bipyramidal. So this can be explained by PCl5. So let's just write that bipyramidal. Now if we go here, we can arrange PCl5 like so. So we have one going into the plane and one coming out of the plane. Now here, if you notice that we can form a triangular base at the equatorial chlorines and then connect one axial chlorine to each vertex. And what that forms is a pyramid on the top. The same thing can be done for the bottom chlorine, and this forms 2 pyramids with the base as a triangle, thus the name trigonal pyramidal. bipyramidal, so there's two pyramids. A steric number of 6 would give us octahedral. So the steric number of 6 gives us octahedral. And an example would be SF6. So we have one sulfur in the middle. Then we've got 4. So we have 4 fluorines like so. And then we have 2 fluorines on the axial position. So again, if you take a look at this, you can draw a square like that and then connect all the vertices to both of the axial fluorines. And what this does is that it creates a 3D shape with 8 faces. So technically it is also planar bipyramidal, but a much better fitting term is octahedral because it has 8 faces in total. And that is it with VSEPR. So in summary, the valence shell electron pair repulsion theory just tells us that in any given molecule, electron pairs are going to position themselves in such a way that they maximize distance and minimize repulsion. Now, here's the thing with VSEPR. It only explains how the atoms are going to be positioned. It never does the job of explaining how the molecule forms in the first place. And it fails to explain the transitional metal complexes. So with the addition of the D subshell and then the D subshell's half and full filled stabilities, and it does not account for orbital energy and hybridization between the atoms. So over here, let's take the example of water. Here we clearly see that this bond and this bond is going to be different because the valence shell in oxygen is going to have both S and P orbitals. Same goes for methane. At least one of the hydrogens is going to match with carbon's 2s orbital. However, when we look at the experiments, we see that all bonds are same. So here VSEPR clearly fails to explain why that happens. And then again, if we talk about delocalized electrons, or in other words, the resonance structures like benzene or carbonate, that again cannot be explained by VSEPR. And that's it for valence shell electron pair repulsion theory.